Okay, so welcome back, guys. This is the 8th lecture, and I'll be talking today, continuing my talk about symmetric positive definite matrices. And as you remember, we started this talk last time after solving the first homework. So basically, this is the outline of the presentation, and I will post the lecture slides later on. So what are symmetric matrices? So we'll talk about the characteristics of symmetric matrices. So we said that all eigenvalues lambda of a symmetric matrices are supposed to be real numbers. And the eigenvectors Q can be chosen to be orthogonal if in your solution computation you are not able to get orthogonal eigenvectors. Well, you still can do. Just doing some simple tricks, among them what we call the Gram-Schmidt method. So in that case, the eigenvectors matrix for S, we can put them in what we call the Q matrix. Q, the eigenvectors, we can put them in a matrix we call Q. And in that case, you can see that Qt and Q inverse are the same. And we've seen that characteristically in the spectral theorem, which was one of the examples we covered in the homework. And we already have the Python code that does that. So basically, you can write S as Q times capital lambda Qt. And I guess that every matrix of that form is symmetric. We can do that. Someone wrote something on the whiteboard. Am I right? We need a Python workshop or review it. Yeah, why not? Who wrote that? We'll get a bonus. Anyways, so one of the properties is that if you transpose this matrix, you get exactly the same matrix. Okay, so you basically verify that the matrix is symmetric. So we've talked about the fact that some matrices could be complex matrices, and in that case, we verify that S is the same as conjugate, the transpose of its conjugates. And for these kind of matrices, we have also the property that all the eigenvalues are going to be real numbers. And we've seen last time, I think the last thing we covered before leaving the class was how to generate the eigenvalues for, or how to write down the code to generate the eigenvalues for a complex matrix. We said that we don't use I in Python, we use J to refer to the complex number. The complex number of the imaginary number. Okay, so basically to verify the orthogonality of the eigenvectors, in that case, we don't multiply the two eigenvectors together. We multiply one vector by the transpose of each conjugate. Okay, in that case, you'll find out that it's 0. And if you did that with the Python code corresponding to what we covered last time, I think it was that part. I'll be sharing it with you. Yeah, this is it. So if we put it here right now, okay. So if you do that, in that case, you'll see that the product of the two eigenvectors that are returned here by the the product of the two eigenvectors returned gives the identity matrix, in fact. So that's for the complex matrices. But let me just run the code first of all, and take a little bit of time because we're not in simple release. So these are the eigenvalues, as you can see, -1 and 8, and you see how the matrix is displayed. And these are the eigenvectors that are generated. The first one is minus 0.816 plus 0j, and minus 0.577 0j. And the second one has complex component. It's 0.408 plus 0.408j, and minus 0.5735 plus minus 0.5775j. So if you take the conjugate of the this eigenvectors matrix and the transpose, you can see that they are the same. And if we do the multiply the two matrices V and V transpose of V inverse by each other, you can find the N or the identity matrix, which is 1, 0. So you have a 0j here, again a 0j here, 10 to the power minus 16 again, and you have 1, 0, 0, 1. Okay, so basically we verified the properties. So this is about the complex matrix, and that was I think the last part we've talked about last time. Okay, so we are all leveled up. So let's start the new material. So here now we're starting to talk about a very important topic in machine learning and data science when it comes to minimization. Well, there is some reason we're computing the eigenvalues, and we need the eigenvalues to be real numbers, in fact. And I will detail, I'll give you quite a few hints on what's going on. But let's briefly talk about these this couple of matrices. So what is a positive definite matrix? In fact, it's a matrix that has all positive eigenvalues. And it is possible to verify that the eigenvalues are positive without even computing them, which is much more interesting. So for example, if you take this matrix, which is 2006, it's obvious that it has eigenvalues 2 and 6. Well, if you just do the determinant of S minus lambda I, you can see that there are only two possible solutions. And you can even use it if you notice that Qt is equal to Q inverse, the same thing as for the eigenvectors we've seen before. So you can see that this matrix also, this new matrix, also taken from the previous one, if you just put it between Q and Qt, have the same eigenvalues. And the same matrix here, S, in fact, helps generating another matrix, which has also positive eigenvalues in case C is just invertible. Okay, so in fact, the fact that you can have matrices with positive eigenvalues can help you generate other matrices with positive eigenvalues, which is quite interesting to notice. Now, let's talk about some of the tests we use to identify positive definite matrices. Can anyone remind us when did you use already positive definite matrices? In which course you already used positive definite matrices tests? Do you recall? And I'm pretty sure everyone.
We have used it in nonlinear programming.
Nonlinear programming, yes. Okay, for those who have taken this course. And what else? Okay, so indirectly, Shabab, you've seen in Calculus 1, when we try to find the critical point and we check that the function is concave up. What are we doing? We're checking the signs of the second derivative, right? So this is one of the correct criteria used, in fact, to identify positive definite matrices, and one of the reasons we're doing this work, in fact. Okay, so first of all, let's talk about what we can call the energy test. The energy test is a test that identifies positive definite matrices, and we can say that a matrix is positive if XTSX is positive for all x's non-zero. Okay, so for example, if you take your matrix S, you plug it between two x and xt and x, and you compute XTSX, you can have here a polynomial. For instance, when x is just in R2. Well, why is that supposed to be positive? Can you tell me, guys? In which cases this is positive? I can plug it here, for example. I can plug it. So I said I have 2x squared. I'm going to share with you an app. Okay. 8x1, x2. And I think I have 9x squared. Okay. So I'll share with you my app. I'll have to take it apart. Okay, can do it now. Okay. Hopefully you can see. Okay. So I've just logged on all from. Okay, I'm not even signed in, and I'm looking this way. What do you guys think? Is it what does this represent? Kind of volume, right? Do you think there is a minimum here for this function? Do you think it's realistic to say that's always positive? Let's take a couple of points, okay? What if I take, for example, the limit when y goes to minus infinity, and x goes to positive infinity? What happens? Imagine that x is going to positive infinity. So what's going on with the 2x squared? Very large and positive. Here, this guy is very large and positive, but what happens between you have a very large negative number, okay? So basically, you cannot conclude here, okay? So there is a problem about concluding on the energy test, in fact, okay? And you see here we have a kind of volume, and it's not easy even to realize it. So there is a problem dealing with the energy test. Okay, so it might be not enough to conclude. Okay, so I'm taking an easier case to get us started. Okay, what about this guy, 5766? Can we write it in a better way? Well, if we do the product, what am I going to have? I'm going to have xt SX, and I'm going to have, in fact, so I'm going to have x1, x2. I'm writing down. Hopefully you can see that I'm writing. Okay. Maybe it's with some delay, but still the most important thing is that it appears. Okay. So what can I obtain? I'll obviously get 5x1 plus 6x2, and on the other part I get 6x1 plus 7x2, and still I need to multiply by x1, x2. So I write down the following. I get 5x1 squared plus 5x1, x2.
6.
Plus, sorry,
6x1, x2.
Yeah, but I have another 6x1, x2 plus 6x2 squared. That's for the product of the first part. When you multiply, am I right? No, I'm wrong. This one should disappear. Okay, plus 6x1, x2. Yeah, and the other part should be 6x1 squared. Okay, plus so 6x1, x2. I'm totally confused. 6x1, x2 plus how much? 7x2 squared. Correct me if I'm wrong. Okay? So I'll finally have something of this kind. 12, I think, x1, x2 plus 7x2 squared. Can you do the math, guys? Check if I'm right. Can you do it? Let's take a couple of minutes and do it, please. Okay, so it's 5x1 squared plus 6x1, x2 plus 6x1, x2 plus 7x2 squared. Okay, so we need the certification that this guy is positive. Again, it's not obvious. Well, there are some tricks. Among some of the tricks we can use is writing, in fact, this polynomial as a sum of two squares. For example, I can write this one as 2 times x1 plus 2x2, okay? And you complete the square. So completing the squares is one of the techniques we use in general. So this is the beginning of a square, as you see. So what would be generated is x1 squared plus 4x1, x2 multiplied by 2, we get the x, we get the 8. And I'll have 4 times 2, I get another 8, and what is left is just x2 squared. So now I have the certification that this guy can only be positive, am I right? For any x1, x2. So one of the techniques one can use here is completing the squares. Is that okay, guys, for you? Hopefully it's clear. So let's do the same technique here. Is that possible? Can we apply the same technique with our thing here, with our polynomial? Let's try. Let's give it a try. Okay. Let's give it a try. So I'll be writing the red. So what can I say? It should be how much? Let me say it's 5. Okay. I'll write 1. Okay. So maybe I should write 2x1, x2. Okay. Or how much? So just want to use all the x1, x2s, I'll be putting how much? It's 12 over 5. Or 12 over, or 6 over 5, am I right? Should be 6 over 5. So 6 over 5 times 2, 12 over 5 times 5, I get the 12. So it should be 6 over 5 here. I'll write it in a better way. So I had 5x1 squared. I had 5x1 squared plus 12x1, x2 plus I guess I had 7x2 squared. So one can write it down as 5 times x1 plus 6 over 5 x2. Okay. So if you square this part already, you get what? You got the 5x1 squared plus 2 times x1, x2 times 6. So 12 over 5 times 5, so it's 12x1, x2. You got this part. And you get also how much? You get 36 over 25 x2 squared. Multiplied by 5, so it's 36 over 5 x2 squared. Okay, so what do you think here? You see, it's already above the 7. Okay, so there is no way I can get it. So I need to subtract how much? I need to subtract the minus 1 over 5 x squared, so we cannot make it. We cannot show that it's going to be positive everywhere. Okay, is that clear for everyone? So we're not able to complete this square like we did at the beginning. Okay, so, but still, even though it might be conclusive in some of the cases, let's say that it's not that interesting to rely on something that is not conclusive all the time. So the most important observation is that other tests exist. And for example, if we can write that S is equal to AT times A, where A has independent columns, we can use what we call the leading determinant test. So what is the leading determinant test? Well, for those who've taken the linear and nonlinear programming test course, they already did that. So first of all, let me talk about the case where S could equal as AT times A. So as the product, AT times A. Well, let's put you back in context. The reason we do all of this, Shabab, is to understand the tricks used later on when it comes to deep learning and machine learning, and why we suppose that matrices has some characteristics. Could be rewritten using some kind of factorization to find the adequate calibration of the smoothing of some functions or the estimation of some functions. Okay, so in that case, in the case where S is equal to AT times A, the question here is why A needs to have independent columns. Well, think about it, that if you're using the energy test, and if you plug, instead of S, you plug ATA, well, in fact, you're doing XTAT times AX, but in fact, this happens to be just the norm of a vector, and the norm of any vector is positive. So if it's not equal to 0, if this is not equal to 0, well, this happens when in fact the new space is not the 0 vector. Am I right? Okay, so the matrices, the columns of A happen to be independent in that case. So the energy length of AX, or the norm of A squared, needs to be strictly positive and not the 0 vector. Okay, and this happens only when the columns of A are not 0. So for example, if you take the following matrix S, which is written here as the product AT times A, this is AT here, I'm pointing to it, and this is A. One can notice that this matrix S is written as T times A, but A has dependent columns. How come A has dependent columns? Well, if you do the following, Shabab, if you take column 1 plus column 3, what do you get? You get 2 up and 4 down. If you divide by 2, you get back column 2, which means that column 2 is just column 1 plus column 3 divided by 2. This matrix cannot be written using, so the columns of A are not independent, as you see here. Okay? And this is for the case where you're trying to write ST as AT times S as AT times A with independent columns. Here we did not succeed, in fact. Okay. So there is another test, which is the determinant test, and this is the test which is mostly appreciated by those who do nonlinear programming, which is the leading determinants test. or consecutive. Sometimes we call it consecutive determinant test. And this is quite easy to understand. This is, by the way, the quickest for small matrices. Why? Because when you have such matrix, it's very easy to compute the leading determinant test. So these determinant, the one as you see in the figure, needs to be positive. What do you mean, the leading determinants? For example, you start by the first submatrix, the one generated by first row and column 1. Row 1, column 1. Then you add a row and a column. You get the next determinant. Here, for instance, it's 3. The next one here, for instance, is going to be 4. Okay? And if you continue on generating all consecutive submatrices here, you obtain the leading determinants. And all these determinants need to be positive to ensure that your matrix is positive definite. Okay? Right. Now, there is a relation between these leading determinants and, in fact, the related pivots. And this relation is quite beautiful because, in fact, if we take this matrix, for example, I'm working on this matrix, and you can see that the consecutive, the leading determinants, here I have 2, am I right? Then the next one, so if I take the next one, I get 4 minus 1, which is 5, positive. So I get 4, which is positive. The next one is going to be 5, positive. And the last one, well, how can I compute that? Well, it's going to be composed basically by 2 determinants. So I'm going to have, for example, for the first one, I'm going to get 2 times this, 2 times 5. And I'm going to get plus 1 times this determinant, the one that gets here with these 2 submatrices. Basically, it's going to give me 10 plus, I'm going to have minus 2. Okay? So it's going to be 8. If you remember how to compute the determinant. So this is for this matrix is positive definite. So if I can use the LU factorization, and I think we already did that, this is the L matrix I can obtain, and this is the U matrix. Okay? So what is said here, what is said is that the kth pivots that we generate, where are the pivots, guys? They are here, am I right? In the U's, huh? What do you guys notice? Okay, so if you go backwards, these pivots, in fact, happen to be in relation with the consecutive determinants we generate. So this is the relation. The kth pivots equals the ratio dk over dk minus 1. Okay? So the k pivots equal the ratios dk over dk minus 1. Am I right? This is 5, 4, minus 1 should have been 3. So that was my mistake. So let me write it again. So the determinants here should be, the first one is 2. Okay. The second one is 4 minus 1, which is 3. Okay. And the last one, I think if I choose the first column, first row, I get 2 times 4 minus 1, so 6. And I'm going to have plus minus 2. So it's going to have 4. It's going to be 4. I made a mistake, sorry for that. So to get a 6, what did I choose? I chose this first element and the following submatrix. So I get 2 times the determinant of 2 times 2 minus 1. So I'll get 2 times 3 gives me 6. And finally, I get the minus 1, so it gives me minus 1, plus 1, sorry. And multiplying the minus 2 plus 0, so minus 2. 6 minus 2 is 4. Okay, so you can see that the leading pivots here, the kth pivots are given by the relation which is dk over dk minus 1. So I have 3 over 2, 3 divided by 2. The next one is going to be 4 by 3. So somehow we are saying that the leading determinants appear when we perform the LU factorization. And this is the most important thing we have to do, is that the leading determinants appear when you do the LU factorization. Okay, which appears to be much more conclusive than the energy test. Right? Any observation, Shabab? You can notice that in the elimination, all the pivots of S are positive, and if all the pivots are positive, you can conclude. But before continuing, one can see that there are some tricks we can do. For example, here, one can pull out the pivots in a matrix D. So we pull them out, and we put them between the two matrices. So we kind of taken these pivots, which are the most important parts, those who can help us certify that the matrix is positive, and put them in kind of an I matrix, identity matrix, but where we have in the diagonal only the pivots. I can do that, and I have two new matrices here. On the side, I have L and LT. This is LT. Okay? This is nothing but L. It's exactly the same matrix, and this is LT. Okay? So we kind of were able to write our matrix as L times dt times LT. Okay? And we can do much more. Okay? So we can share those pivots on AT and A. Okay? So remember, the whole purpose is to write S as equal to AT times A. Okay? So what we did is we shared them among these two matrices. So basically, what we did is the following: is that write down S as L times root of D times root of D LT. So being we get the D. Okay. So we kind of, if we go back to the previous slide, you see that the root here is going to be root of 2. Here is going to be root of 3 over 2. And here is going to be root of 4 over 3. Okay. And we apply the roots, of course, here. So it's going to be minus root of 1 over 2, minus root of 2 over 3. Here again, minus root of 1 over 2, minus root of 3. This is how we obtain the matrix A. So this is a methodology one can follow to obtain these two beautiful matrices, AT and A. Okay? So these two matrices, one is the transpose of the other, and they have independent columns. If they have independent columns, it means that we can conclude that the matrix is positive symmetry. Okay? And this kind of factorization has a name, the Cholesky factorization. Cholesky factorization. For those who are very familiar to chess, I'm thinking chess as a game, I think there is a very famous move called Cholesky move, if you know about in chess. So Cholesky factorization, what it does is just basically takes the absolute values, the square roots of pivots on the main diagonal of A and AT, okay, and puts back the roots we obtained in the other sides. Okay? So to apply the S equals AT times A test, when S is positive, definitely we need to find at least one possible with an independent colors. Of course, there could be choices for A, including symmetric triangular, as in this symmetric or triangular matrices. So, for example, for symmetric, we can use spectral factorization. Okay, and you can here assume that, for example, that A is equal to Q root of lambda QT times AT. It should be, I think. Or you can use a triangular, like in this case, where it is a Cholesky factorization. So all of that is to say that, in fact, there is some reason we're doing all of this stuff, Shabab. Well, there is some reason we would like to deal, we prefer to deal with matrices we have positive real eigenvalues. It is the context of minimization. So if you remember, in Math 101, one of the reasons we could conclude that a function is concave upward and it has a minimum, whether absolute or global, was about the sign of its second derivative. Okay? When it happens to that we talk like in Math 2.1, we talk about functions with many variables. It's enough. So we don't need to compute only the second derivatives. Okay, we need to compute the derivative of a function with respect to the second derivative with respect to all the variables, x and y, for instance. Here. So the first order condition sets the fact that we have a stationary point or critical point, a point where the first derivative is 0. Okay, sometimes in some textbook you can write it as gradient here of f is equal to 0. So if the gradient is equal to 0, it means that basically you have a horizontal tangent to your curve. Okay? So imagine this is a 3D curve, of course. But this matrix, in fact, the one that with entries all defined by the second derivative is called the H matrix. H for Hessian matrix. Hessian for famous mathematician, and it's called like this for H matrix. Well, the entries are the second derivatives. So the graph of the function given by f of xy is flat at that point x0, x0 because of the first order condition, and it goes upward because of the second derivative matrix called the Hessian matrix. That needs to be positive semi-definite. Okay? So immediately, we're going to see two examples that ensure that we have this condition. For example, in the first example here, where I have f of x equal 5x squared plus 5y squared. Okay? If you compute the first derivative with respect to x, you get 10x for sure. And if you compute the first derivative with respect to y, you get 10y. So if you want to find the point where the first derivatives are both equal to 0, the only solution here is to set x equal to 0 and y equal to 0. I think it's pretty obvious. If you compute now the second derivatives, the second derivative of f with respect to x is giving you the derivative again of 10x with respect to x, which is 10. And if you differentiate it with respect to y, of course, you get a 0. So this is the f with respect to x, then with respect to y. So it's the second derivative, first with respect to x, then the respect to y. If you differentiate the 10y with respect to x, of course, you get 0. And if you differentiate the 10y with respect to y, you get a 10. Okay? So this is what we call the Hessian matrix. The matrix we need to study to certify whether or not it is positive definite and conclude whether or not we have a minimum at that point, 0, 0. Okay? So this matrix, this Hessian matrix needs to be positive definite, or sometimes we relax the condition if we say it's positive semi-definite. So some of the leading determinants could be zeros, for example. To conclude, in that case, you see that we have an absolute minimum, in fact, at this point, which is the point 0, 0. It lies really at the bottom of the value at the point 0, 0. Okay? Right? And it's obvious that the leading determinants here, what are the leading determinants? First one is 10, صح? And the second one is 10 times 10. So we get 100. So the first leading determinant is 10, and the next one is 100. Okay? Again, the eigenvalues here are going to be repeated. It's unique, it's 10. Right. What about the second example? With the second example, I have 3x squared plus 2y plus 4y squared as my function. If I compute the first derivative, I have 6x plus 2y. And on the other side, if I differentiate with respect to y, I have 2x plus 8y. So the first derivative of f with respect to x, 6x plus 2y, 6x plus 2y. Why? Because when you differentiate the 2x with respect to x, you get just 2y. And if you differentiate the f here with respect to y, the first part gives you 0, then we have 2x plus 8y. Okay? So you need to solve a linear system, a homogeneous linear system where 6x plus 2y equals 0 and 2x plus 8y equals 0. Now, can you answer this question? Why does this system has only one solution? Let's see if you are understanding. Why does it have, why does the other say that we have one solution? Are you with me? Are you with me, Shabab?
Because both columns are independent. So the only solution here is 0.
Exactly, because both rows are dependent and or both columns are dependent. Excellent, Firas. So the matrix here 6, 2 to 8 is invertible, so there is a unique solution, which is 0, 0. Excellent. So, but more than this, if we compute the Hessian matrix, plug in the second derivatives here, all 4 second derivatives. By the way, you will always have the f, d squared f over dx dy, always equal to d squared f over dy dx. So if you, it doesn't matter whether you differentiate with respect to y first or x first, you always end up with the same value. Okay, so you get 6, 2 to 8. What are the leading determinants here? The leading determinants are, first one, d1 is how much? Is 6, so? And the second one, d2 is going to be the whole determinant of the Hessian matrix, which is 48 minus 4. It is how much? It is 44. So both of them are positive. And since they are positive, we can certify that this point, this matrix, first of all, is positive definite. And this says, in fact, the absolute minimum. And if you plot the graph here, I used Wolfram to compute to plot the graph. You see that the 0, 0 here lies at the bottom of the curve. Right? Now, I have a question for you. Can I do this Cholesky factorization on this matrix? So can I basically write it as, can I write S as AT times A with linear independent columns? Or can I use the energy test? So this is one of the tests. The energy test says that xt times sx is always positive. So this is the energy test today, Shabab. This is the symmetric matrix test, where AT times A equals S with independent columns. Well, there is another test, the leading determinant test. Okay? And finally, what else? After the leading determinant test, we've seen another test, which is the, what else? The Cholesky factorization. Yeah, well, it gave back the AT times A. So the question here, can I use the LU factorization first of all? So if I have 6, 2, 2, 8, how do I get the LU factorization? First of all, I need S to be written as, what are the pivots here? So I get L as 6, 2, then what is the next part? I get 0, صح? And so basically you need to find me this number, right? So how much is it?
8 minus 2.
8 minus 8 minus 2 over 6 times 2, صح? So it's 8 minus 4 over 6, yani 8 minus 2 over 3, which is 22 over 3. Okay? Okay. So what do I need to place here? The first determinant obtained was so I'll let you finish. So what do we need to place it?
The diagonal will be 1, 1, and the lower entry C21 will be the multiplier, which is 6/3, 2.
You mean this one?
Yes.
This one should be sorry, 6, 2. Okay. I think this one should be how much? 20. How much you said? 1/3, right?
Yeah.
Am I right this way?
Yes.
Oh, but this. So what is wrong here in my factorization? Let's correct. Is it right what I'm writing? Is it okay?
No,
No.
it's L and
No.
L.
Why is that okay?
We need LU.
Okay. So let's correct that. So first of all, the L should contain the
Lower triangle.
okay lower triangular. So it has to be here. What should I put? Said 2/6, and 1/3. Am I right? Okay. And what should I place in this case? I'll have 6, of course, a 0 here. And what is next? I'll have the 44/6, and 22/3. Am I right?
What's the original matrix?
It was 2668. 6228, sorry. Okay. So I get the 6. What else I get?
6 also.
Here 6.
No.
Get 6.
2. The remaining one is 2.
So this way I get 6. I get the 2. I get the 2, and I get 2/3 plus 22/3, 24/3. So this is the LU factorization. You can see that the leading determinants are here. Okay, we can take these and put them in the diagonal. So I can write it like this: 1, 1/3, 1, 0, and here in between I'll get 6, 22/3, and again I'll get the transpose of this. So 1, 1/3. 0, 1. Beautiful. Okay. And what else? Now I can get the roots. Okay. So basically, I get the following matrix, which is here I have root of 6. Yeah. Here I have root of 1/3. And here I have root of 22/3. So this is AT. And for A, I'll have how much? I have root of 6 also. On the other side, I have root of 1/3. I have 0, sorry, and root of 22/3. So you can see that these two matrices, they satisfy the condition that AT times A equals S, and they have linear dependent counts. Okay? So let me quickly get the attendance, Shabab. Before we go, Mohammed Abdurrahman, Abdulaziz Al-Sumbul.
Yes.
Abdurrahim, yes. Abdulaziz Al-Sumbul موجود.
Yes, sorry.
سلطان العبودي.
Yes, doctor.
أهلا وسهلا. خالد العبدية.
Yes, here.
حسن سعد.
Yes.
عبد الإله العرفج.
Yes.
فارس الحسن.
Yes.
عبد الرحمن الحسين.
Yes. Yes.
محمد الجالوت.
Yes.
عبد الله القريني. sorry.
Yes.
ثامر العتيبي.
Yes, doctor.
عبد العزيز الراشد. عبد العزيز راشد. فراس موجود. عبد الله الرقيعي موجود او لا؟ عبد الله.
Yes. Yes.
حاتم ارويس.
موجود يا دكتور.
نواف الشهري.
موجود دكتور.
فيصل السبيعي.
موجود يا دكتور ياسر السبيعي.
زياد باس. زياد. يوسف بنتن.
يس دكتور موجود.
يوسف.
موجود يا دكتور.
يوسف موجود. عبد الله باروم.
موجود.
اوكي. اوكي. That is having mic issues. عبد الله باروم موجود. خالد باسودان.
Yes. دكتور.
ريان كعكي. نعم.
زياد زهير.
يا اوكي. ريان كعكي موجود.
راكان كعكي دكتور موجود.
سوري راكان. سوري. محمد السليم. سوري.
موجود.
اهلا وسهلا. طيب who's not there؟ عبد العزيز. I'm calling again.
العزيز موجود دكتور.
اهلا وسهلا. طيب okay guys, so see you next time inshallah. I'll post an announcement regarding the quiz we'll have by the end of the week inshallah. Okay, so we'll talk about it Thursday inshallah. Till then, stay safe and take care of yourself. I'll post this material inshallah. Yeah, assalamu alaikum. If you have any question you can ask guys.
Doctor, if you can share the link of the recorded session.
Yes, of course, I'll do. My pleasure. Yes, Tamer?
The quiz will be in the end of the week, or?
Whatever you wish. It's going to be on the end of the week, inshallah.
We're going to discuss.
Probably Saturday night.
Okay.
The material is going to be from, the material is going to be from, we said 10.1 till 10.7 or 8, I think we said. Okay?
Okay, great. Thank you.
So part of the material which was covered in the first homework and the new material. Okay? Bye. Okay, guys. See you. Assalamu alaikum.